Now here's another way we need to rearrange our integrand. And this is one where we've got 1 over a square root, or something over a square root of a function. Now, when we come down to these ones, really it's going to come down to when we integrate, we're going to come to two things, an inverse sine or a log function. But again, keep going back to your table of standard integrals, because the log functions are some of those weird ones at the end of it. So you need to be able to look at those. I don't remember those ones off by heart. Not many people do, because they're a little bit difficult. So you need to be able to look at it and be able to get the square root of the number. And it's either, if it's going to be a minus there, it's going to be an inverse sine function. If it's a plus there, we'll end up with, you can see in the next one, with that log function. So you get that's what we're going to look at. So the idea here, again, we can't get it back to something where we can take the square root of it and it clears out. So we've got to be able to manipulate our function here. So we've got the 7 minus 6x minus x squared. Again, we want to get back to that idea of a perfect square, because once we've got that under the square root, we can get an inverse sine function. So the manipulation here, we take them, and have a look what I've done. I haven't shown it much in that, so I've added this one here, 7 minus 6x minus x squared. I could rewrite that with take the minus x out there, I get the minus x squared plus the 6x there, and I've got a plus 7. So if I'm going to do this, I'm going to have to, in the bracket here, add the 9, but really I'm adding a minus 9. Because to put it in the bracket, I've got the bracket out negative out the front, which is really a minus 9. And then I've got to add a 9 there. So that's where we get the 16 from. So if you're wondering, well, how do you get that from that part to that part? That's where it comes from. Because I've just rearranged it, because I'd rather work with a positive x there. But there's the minus x plus 3 all squared plus a 16. So that's how we can write it there, which is in the form that we need for the inverse sine function. So that's how that one gets manipulated there. So this one's a little bit easier in terms of the manipulation, because it's 9x squared plus 9. Well, you can factorise the 9 outside of x squared plus 1. The square root of 9 becomes the 3 outside the x squared plus 1. And if you have a look at your table of standard integrals, square root of x squared plus a number would give us that as our standard integral. So again, that's where we need to keep going back and checking and using our table of standard integrals as we go through. This one, a little bit of manipulation needed, and the manipulation is going to come in the form of a substitution. So if I let u be equal to x plus 1 in this case, I'm only going to do that after I get down to the x plus 1 all squared plus 3, because if you have a look at your table of standard integrals, you get a function, just the term squared plus 3 there to get that function. So we need to be able to manipulate it a bit. That's why I've gone with a substitution. Let u be equal to x plus 1, and that comes from there. X would be u minus 1, so that's where I will do the u minus 1. Du is dx. So we get u minus 1 du on the square root of u squared plus 3, which gives us a situation where it's just the u on the square root of u squared plus 3. Now remember our reversal of the chain rule. So d dx of a half, and that would integrate, because minus a half, integrates to a half. And we'd have the u on the square root of u squared plus 3. So that's one. It's going to pop up a number of times. So it's handy to, if not be able to know it off by heart, going from that part to that part, then recognizing that it's a possible reversal of chain rule. So differentiating square root of u squared plus 3. So only because you're going to see it in a number of different questions. So be wary of that manipulation. And then that's going to be 1 over the square root of u squared plus 3, which is, by our table of standard integrals, is the natural log of u plus the square root of u squared plus 3, plus our handy constant of integration. And then we can substitute out x plus 1 back in for u to get that expression. Now, that's a bit nasty. So a little bit of manipulation needed. Actually, not a little bit, a lot. So we've got to be wary of how we can manipulate it, because some of them are going to be hard. You're doing extension 2. It's going to be hard at times. This time we've got x plus 2 on the square root of x plus 1 plus x plus 1. Which again, if we manipulate it down, I need, because it's 1, I need the quarter. So 1 can be split up into a quarter plus 3/4. And when I've got x squared plus x plus a quarter, that's a perfect square of x plus a half all squared. Plus the 3/4, which again is going to be x on that function and 2 on that function. Well, that's going to come down okay, because we've got it. That's not a bad manipulation, but this one's going to be a little bit more work. So pay attention. Let's have the u is equal to x squared plus a half, x plus a half. So x would be u minus a half, and du is equal to the x. So we do that substitution. The u on the u squared plus 3/4 power half. Again, realize that is a manipulation of the reversal of the chain rule. This one's just a genuine polynomial as such. So, and we can get, without having to worry about the u there, we can just get the 3 on 2, because it's a half minus a half plus 2, so it gives us plus 1.5, which is going to come down to, using our table standard rules, that 3 on 2 natural log of u plus the square root of u plus u squared plus 3 on 4 plus the constant, and that's a reversal of the chain rule. So again, see, we said it was going to come up with, and it has. Let's come up again. Next question. And then, so we can then do our substitution of u back for x plus a half. Again, not easy. Be really careful with it. Learn these manipulations that you can do. So this time the 2 minus x squared. Again, I've manipulated to get the minus x squared plus x, which I'm going to have to add a quarter to get the perfect square. Actually, I'm subtracting a quarter here and then adding a quarter. So that's where the 2 1/4 comes from. And we get the 9 on 4 minus x plus a half. And then doing the then from our table standard integrals, it's an inverse sine function, which comes down to that manipulation once we do the cleanup of the algebra in the fraction. Again, similar to the last one, we can see our manipulation here. The minus x squared plus 2x gives subtracting 1 here and then adding 1. So we're able to write as x dx on 2 minus x plus 1. Now, because if it was just 1 over that, not a problem. That's just going to be a straight inverse sine function. But it's not, because it's an x there. So we do a little substitution. Let u be x plus 1, which is going to make our denominator a little bit simpler. Our numerator is a little bit harder, but not too much, because it allows us to split it up when we just got the u on top, or the square root of 2 minus u, and which again is going to be coming down to reversal of the chain rule, and the 1 on the square root of 2 minus u, well, now that is an inverse sine function, which we're able to get the integral there and do our substitutions back in. So there we go. There's some substitutions and some manipulation of our denominators when we have square roots there. As I said, it comes down to the sine functions, inverse sine functions, or those log functions. But be wary of a reversal of the chain rule, which comes up in some questions as well. So we've got to start to put a number of integration techniques together to solve some problems. Relying on us to manipulate algebra, do some substitution, reversal of chain rule, and keeping in mind our table of standard integrals. So look through those again carefully. Get some practice in. So hopefully, no matter what type of integration problem faces you, you're able to realize as quickly as possible what manipulation you need to do to solve that problem.